everyone. I'm going to introduce our speaker today. Thank you, Juliet, for running this awesome series and opportunities to bring amazing speakers to campus. And I'm excited today to introduce Dan Lee, who's a professor at Boston University in Earth and Environment. And I also learned while preparing an introduction to introduce Dan that he's also a professor in engineering. So he has his PhD in engineering, civil engineering from Princeton, and came to BU in 2016, I believe, right?
Almost a decade ago.
Almost a decade ago, to be a professor. And I'm so excited to share with you some of the amazing kind of recognitions of Dan's work. So Dan is broadly focused on the dynamics, thermodynamics of the atmospheric boundary layer, and applying that knowledge to understanding how to solve really pressing sustainability problems. As his talk title suggests, he works a lot on understanding impacts of urban heat and a lot of urban climate issues, and how can we actually apply that knowledge on the ground. And so he's consequently been recognized quite a bit for all of his incredible work. Some things I learned: he got the Humboldt Fellowship for Experienced Researchers. In 2022, he got the Timothy Oak Award from the International Association for Urban Climate. And also in 2023, from the American Geophysical Union, the Global Environmental Early Career Award, in just recognition, not of just his contributions to his specific discipline, but what I'm really excited about working with Dan is also thinking very broadly about working across disciplines to really get leverage our scientific understanding of systems for solutions. So with that, now that I've got you all hyped up and excited to learn about what Dan has to tell us about bridging the gap between applied meteorology and climate science with a few urban modeling examples.
Okay. Thanks, Joy, and thanks everyone for coming to my presentation. As Joy just mentioned, my name is Danny, and I'm an associate professor in the Department of Earth and Environment, and also Department of Mechanical Engineering at BU. And the title of my presentation is Bridging the Gap Between Applied Meteorology and Climate Science, using a few urban modeling examples. Before I get started, I want to just take a quick minute to introduce my research group, which is called the Environmental Fluid Mechanics Group. These are the keywords of the papers that we publish in my group. As you can see, a few things really stand out. We study quite a bit of this atmospheric boundary layer, which Joy just mentioned. It is the lowest part of the atmosphere that's directly influenced by the surface, and it's typically from the ground to about 1 to 2 kilometers high. And a lot of the work that we do is in the urban environment. For example, this urban heat island effect that many of you probably are familiar with, and is something that I will be talking about today, is a topic that we study quite a bit in my group. So overall, we study the dynamics and the thermodynamics of the atmospheric boundary layer, and how understanding those dynamic and thermodynamic processes can help us address real-world sustainability challenges, such as urban heat. With that, I also would like to acknowledge funding support from all these different agencies. So to begin, urban meteorology and climatology is often viewed as a branch of the applied meteorology and climatology. That's because urban meteorological and climate information is so critical for so many real-world applications, such as the design of buildings, the operation of drones in cities, which you probably will be seeing happening anytime soon, and then the development of climate adaptation plans. All of these activities require urban meteorological and climate information, especially the design of the buildings, which is kind of like the one branch of mechanical engineering that dates back to very, very early on, right? So in 2005, there was actually a paper published on BAMS titled "Applied Climatology: The Golden Age Has Begun." And interestingly, I'm showing you the number of articles on urban heat mitigation, which is only a small topic under the umbrella of urban meteorology and climatology, which then it's only one branch of the applied meteorology and climatology, right? You can see that the number of articles on urban heat mitigation also increased quite sharply after 2005, which sort of suggests that we are really in the age of golden age of looking at or studying applied meteorology and climatology. So one of the reasons that you see the increase of number of articles on urban heat mitigation, as well as other topics under the umbrella of applied meteorology and climatology, is also because we oftentimes approach these problems from the applied perspective. For example, when it comes to urban heat mitigation, we often study the effects of urban heat mitigation strategies for different cities, for different time periods, for different configurations of mitigation strategies. So whenever we change a city, change a time period, change a configuration, you can almost argue that you generate a new study. So not too surprisingly, I also contributed a few studies into this trend. I did my PhD. I finished my PhD in 2009. When I started my PhD around 2009 and I finished in 2013, where I was looking at the urban heat island effect in Baltimore, Washington area and its mitigation using white roofs and cool roofs. At that time, the question was like, if you have a certain fraction of white roof and cool roofs, how much temperature change you will expect or you can obtain from numeric models. And then I did my postdoc from 2014 to 2016 at GFDL, which is the place where we built the first global climate model. So I implemented an urban modular into the land model so that we can simulate urban climate in these global models. And then using those urbanized global land models, I looked at the simulated urban climates, at much larger spatial scales, continental, global, etc. So you can see that sort of like, my PhD and postdoc period really coincides with this period where this, trend starts to accelerate. However, what I'm going to talk about today is actually different from the research that I did during my PhD and postdoc period, much because as I spent more time, in this domain of looking at urban heat mitigation strategies, for example, I started to realize there's a gap between applied meteorology, where we look at things through the lens of, applied with climate science, where we, really trying to understand the problem. Obviously, there have been many giants in our field that talked about this problem in a much larger context. Look at, for example, the gap between understanding and climate simulation in general. And all of these papers, some of which are showing here, really motivate me to re-examine some of my own research, which of course more specifically focus on the urban climate and urban modeling. So today I'm going to use 3 examples, 2 of which I actually studied when I was doing my PhD, white roof, green roofs, to show you some of our recent attempts trying to kind of like bridge this gap between looking at everything from the applied perspective versus climate science, where we're trying to actually understand the effects of these mitigation strategies. I'll start with this white roof problem. There have been a lot of studies using numerical models to quantify the effects of white roofs, as compiled by this recent review paper by my friend Scott Kreinhoff in 2021. So you can see that in all these papers, they're trying to use this index called albedo cooling effectiveness to quantify the effects of white roofs, which is defined as the change of the temperature due to white roofs, normalized by the change of the albedo at which the temperature is defined. And in all these models, the temperature is typically defined at the so-called grid cell level, and you will hear this word a lot in my talk. So the change of the albedo at the grid cell is like the change of albedo of the roof multiplied by the roof fraction, because you only multiply the roofs. The negative sign is basically recognizing that when you increase the albedo, you tend to reduce the temperature. So when the delta T is negative, with the negative sign, you make the ACE values positive. So in my presentation, I use this delta quite a lot. It always means a change. For example, in this context, it will be a change of the temperature due to the white roof. So if you look at the review paper, they compiled a list of what they call high-quality numeric modeling studies, one of which was actually done by me when I was doing my post-PhD, the Lee et al. 2014 paper here. They compiled a list of ACE values, and you can see that the ACE values really range, from values are like 0, basically not much effect, to as large as like 20, right? With the majority in this range of like, 1 to 5-ish. So if you look at, for example, the paper that I published almost, more than a decade ago now, like the range is roughly between 2 to 5, something like that. The problem with like compiling a list of these ACE values is that it gives the wrong impression that the ACE values might be a constant, so that we can apply it any way we want, or we can take the values in the literature and then we can use it, somewhere else during some other period. So let me begin by saying that the ACE cannot be a constant. It should be, at the very least, vary with the amount of solar radiation the roof receives. A thought experiment tells you that in places where you get a lot of solar radiation, a lot of sun, changing the albedo of the roof or any other material surfaces will make a stronger difference than in places where you don't get a lot of solar radiation, right? Imagine in a completely dark place, changing the albedo is going to make 0 difference. So the ACE values cannot be constant. In that sense, we should not be taking ACE values from the literature and then apply it to whatever study places that we are doing. So the second, which is a bit more subtle issue, is that because we're so interested in particularly the health effects of these mitigation strategies, oftentimes we very much focus on the so-called near-surface air temperature, because that's the air temperature that you feel, and that's the air temperature that is used in a lot of the assessment studies with respect to health effects. However, the change of the near-surface air temperature often tends to be very complicated, mostly related to the movement of the air in the near-surface air, right? So I'll show you an example to demonstrate this. So let me give you an example of how a typical white roof study looks like in the literature. So we use numerical models, and these are essentially computed codes that allow you to sort of like assess the effects of, like, say, white roofs or other things without actually constructing a white roof in the reality. So for example, in this model called the Weather Research and Forecasting Model, WRF model, is actually the model that we use for weather service, weather forecast these days. It has a single layer urban canopy model that sort of like conceptualizes the urban environment like this. So you have a impervious component and a pervious component treated often as grassland. And then the impervious component is often conceptualized as sort of like a canyon. So you have a building and then you have a canyon floor. So the roof of the building directly talks to the atmosphere that's supposedly above the canyon, and in the numerical model is typically about like 20 to 50 meters high. And then the wall of the building and then the ground of the canyon, they talk to this canopy air temperature or the canyon air temperature, and then talks to the atmosphere above the canyon. So you can see that in this model, the roof is explicitly represented, right? So you can sort of like, increase the albedo or the reflectance of the roof to sort of mimic the effect of white roof in these simulations. And if you do so, you probably would expect that as you increase the reflectance of the surface, the temperatures near the surface are going to be reduced. So imagine for such a complicated grid cell, or what we call urban grid cell, you can have an urban surface temperature. It's not often well defined, but imagine you have a well defined surface temperature. Its temperature is probably going to be reduced when you increase the reflectance of the surface. And the cooling signal is probably going to propagate into the atmosphere. So the near surface air temperature, which we all often use this 2-meter air temperature to represent, is going to be reduced. And then the temperature above the urban canyon might also be reduced. So that's kind of like what we normally would expect. However, the atmosphere is a chaotic system. So sometimes unexpected things happen. For example, if you accidentally induce some warm advection into the regions where you actually construct a white roof, the temperature above the canyon might actually increase because the warm advection that is, accidentally caused by the random and chaotic movement of the atmosphere, especially at short time scales, then the surface temperature might still be reduced. However, the near surface air temperature might actually be increased because of the chaotic nature of the atmosphere. So let me show you actually real simulations that we did using the model that we use for weather forecasting these days. This is the Great Boston area. I can't really tell where NOAA is, but it's probably somewhere here. But you can see that this is the ocean, this is like Boston. I did this simulation at 1 kilometer resolution over a heat wave period. The top row is the near surface air temperature averaged over this 5-day heat wave period using two scenarios. One is the roof albedo of 0.2, which is kind of like the regular roof case. This one is the roof albedo of 0.6, which is the high, white roof case, if you will. And the bottom left shows the difference between the two runs. And most of the places you see blue color, which indicates the temperature is reduced, as you would expect. In some places, you do see surprisingly increasing temperature. And that's because of this chaotic nature of the atmosphere that I just mentioned. So you can actually compute the ACE values as in the literature, as defined in that review paper. And you can see that there's a spatial variability of the ACE value. Different places show slightly different ACE values. They range between about like 0 to 5 or 1 to 5-ish with a median value of a 2.2 Kelvin. So, for those of you who just want to take these results and use it, you would say, oh, our values are perfectly in line with the table that the literature review paper, compiled. We are in good shape. But obviously, there are very good questions you can ask, right? First of all, if you look at the ACE values, why are there places negative values? Or why are some places showing positive increase of temperature when you have white roofs? Second, why is there spatial variability in the ACE values? Can we understand the spatial variability in the ACE values in a domain that is actually pretty small by, weather and climate scales? So the first thing that I did was to address the question of this positive negative change of the temperature. So I did a decomposition analysis of the change of the near surface air temperature, again, this T2. On the left, you're looking at the decomposition analysis for the expected scenario where the temperature is reduced when you have white roofs. So the change of the temperature is negative. On the right is the grid cells in which the temperature change is positive, so the surprising cases. The way to interpret this decomposition analysis is that the first two bars, one are the total effects, meaning that one is computed based on the Wolf model that I just mentioned. The second bar is computed based on this decomposition analysis. And the fact that they reasonably agree with each other tells you that the decomposition analysis is reasonable. That's basically what it means. And then the 5 bars follow the individual contributions to the change of the near surface air temperature. So you can see that for the negative cases, most of the contributions coming from the roof surface temperature. So basically, when you increase the albedo of the roof surface temperature gets reduced, and then the cooling signal propagates into the atmosphere. And it also causes the atmospheric temperature above the urban canyon to be also reduced. On this end, if you look at the positive cases, the roof surface temperature is still reduced, so there's a negative contribution. But the atmospheric temperature above the canyon is increased, as I alluded to earlier, so you sort of have some, unexpected warming signal in the atmosphere that is, instigated by the white roof perturbation that you put into the model. As a result, you cause this really unexpected behavior of the change of the near surface air temperature. So when I look at these results, I was like, why do we have to fixating on the near surface air temperature, even though I recognize that it's super important? But for this problem, shouldn't we take a step back and ask the question, why is the roof surface temperature change in this way? So if we can understand the roof surface temperature change, then we might be able to understand the near surface air temperature change. If we cannot understand the roof surface change, which is the source of the cooling signal, there's no chance for us to understand actually the near surface air temperature change, right? So let's take a step back and just look at the roof surface temperature. So I asked the model to put the roof surface temperature for me. So again, the top row are the roof surface temperatures for the two scenarios. The bottom left is the roof surface temperature change. You can see that all the places are negative values, which is good. At least we're not dealing with surprising situations for now. So it becomes a simpler problem. All the ACE values are positive, and we can even define an ACE just for the roof surface temperature. So I'm using a subscript S to indicate that it's just for the surface. So it's the change of the roof surface temperature normalized by the change of the albedo of the roof. It's mostly positive. It's all positive, actually. But now the question is, can we understand the spatial variability in this map, right? It becomes an easier map compared to the previous one. Well, I've already also told you that one of the reasons that these ACE values cannot be constant is because certain places receive more solar radiation than other places. So the second guess that you probably have right now in your mind is that, well, the variability in the ACE values are probably due to the radiation. So if you plot the ACE values that we just computed as a function of the incoming solar radiation that the roof receives, not surprisingly, there's a really good correlation. In places where you have more radiation, the white effects are stronger as measured by this index of albedo cooling effectiveness for the surface. So if so, then why don't we normalize the albedo cooling effectiveness by the incoming solar radiation if the large portion of the spatial variability is caused by the incoming solar radiation? Let's do this normalization. So let's normalize the ACES by the incoming shorter radiation. And then I'm going to call this a new concept called albedo cooling sensitivity. And I'll tell you in a minute why I call it a sensitivity instead of effectiveness. So this is the result. You can see that now two things I want to highlight. First of all, the unit has been changed. It used to be just Kelvin because the temperature change is Kelvin, the albedo is unitness, but now it becomes Kelvin per watts per square meter. Second, there is still some spatial variability in the domain. It's not a constant. It varies between 0.03 to 0.045-ish. So the question is, if there's still some remaining spatial variability, what causes the spatial variability in this part, in addition, to the solar radiation, right? So the solar radiation variability has been taken out. So now I have to tell you a little bit about the theory behind white roofs using the so-called surface energy balance. The surface energy balance describes nothing but the energy gained by the surface has to be equal to the energy transferred out of the surface. If you think of the surface as an infinitely thin layer, at the top of the roof, an infinitely thin layer, then you can write the surface energy balance equation this way. On the left-hand side of the equation, you have the energy gained by the surface, mostly coming from radiation, so incoming short radiation from the solar radiation, incoming long-wave radiation from the atmosphere. Here we want to subtract the so-called reflected radiation, right? So we multiply the incoming short radiation by 1 minus alpha, where alpha is the albedo of the roof or the reflectance. So 1 minus alpha would be the absorptivity, how much is absorbed by the surface. And then we multiply the incoming long-wave radiation by epsilon, where epsilon is the emissivity. This is because Kirchhoff's law tells us that the absorptivity is also the emissivity in the long-wave band. So on the left, you're basically having the absorbed radiation by the surface. On the right, you have 4 different terms. The sensible heat flux, the heat that the surface used to heat the atmosphere. The latent heat flux, the heat flux that used to change the water from liquid water to water vapor or associated with the evapotranspiration process. And then the conductive heat flux for roof, it will be conducting into the deep roof layers or even the building interior. And then the emitted outgoing long-wave radiation, which is expressed here using the Stefan-Boltzmann law, where sigma is the Stefan-Boltzmann constant and Ts is the surface temperature. So this equation might look slightly different from an equation that you're probably more familiar with, where this term is put on the left-hand side of the equation. Then the left-hand side of the equation becomes the so-called net radiation. I didn't want to do so because I want to emphasize that each term on the right-hand side of the equation is a function of the surface temperature, while the terms on the left-hand side of the equation are to the first order, not a function of the surface temperature. So you can treat it as sort of like the forcing to the surface. And to make the math easy, I'm going to assume all these functions are just linear functions. So they can all be expressed as some lambdas, which represent the slopes of those linear functions, multiplied by the surface temperature plus some c's, which represent the slope, the intercepts of those linear functions. And for those of you who study meteorology, this would be, meteorology 101 for you. We often use a bulk parameterization for the so-called sensible heat flux, how much heat going into the atmosphere. So it's often expressed as rho Cp, the air density multiplied by the heat capacity of air, multiplied by some heat conductance or turbulent heat transfer coefficient, and then multiplied by the difference between the surface temperature and the air temperature. So if you look at this equation, it's just actually a linear function of the surface temperature. So the lambda h here is actually a rho Cpch. The other heat fluxes are not really linear functions of the surface temperature, but we can linearize those functions. In fact, in climate change, we do that very often to the emitted long-wave radiation, which is the surface temperature to the power 4th, so not a linear function. But in this case, we can linearize it around air temperature, so it becomes a linear function of the surface temperature, and lambda ELW, where ELW refers to emitted long-wave radiation, becomes 4 epsilon sigma T to the power 3rd. So these lambdas have units of watts per square meter per Kelvin. They can be interpreted as heat transfer efficiencies. They are very important in my presentation, so keep an eye on them. For example, this lambda H is called the convective transfer efficiency in building engineering or in mechanical engineering literature. But if you're more familiar with the climate change literature, they're actually equivalent to the so-called climate feedback parameters. For example, this lambda ELW is actually the so-called Planck feedback parameter. It represents the strength of the Planck feedback. And the Planck feedback means if you give the Earth system a bit more energy, the Earth system has to increase its surface temperature in order to emit more long-wave radiation back to the space to balance the actual energy it receives. Okay, I understand most of you probably don't like equations and the dry material, so I'm going to use a diagram to help you understand all of these. So I'm plotting the total fluxes on both sides of the equations as a function of the surface temperature. As I alluded to earlier, the left-hand side of the equation to the first order is not a function of the surface temperature. So when you plot it as a function of the surface temperature, it's just a flat line, which is what this black line represents. The right-hand side of the equation, since every single term becomes a linear function of the surface temperature, then the sum is a linear function of the surface temperature with the slope of the sum of the lambdas. You can immediately guess that the surface temperature has to be at this intersection because it is only at the intersection that the left-hand side of the equation is equal to the right-hand side of the equation. In other words, the energy is imbalanced now. Now we can ask the system, what if we, paint the roof white, change the system? If you increase the albedo of the surface, you bring down the black line because the black line represents the left-hand side of the equation, and the left-hand side of the equation is a, a function of the albedo and with a negative sign. So you increase the albedo, it drops. And you get a new crossing point, in this case, a reduce the surface temperature. And that's what you would expect when you increase the albedo, the surface temperature reduce, right? You can do the math a bit more rigorously. You can say, okay, the increase of the albedo is dot alpha. So the change of the black line to the first order is the incoming short radiation multiplied by minus dot alpha from the left-hand side of the equation. And then from simple geometry, you can back out the change of the surface temperature, which is basically this term divided by the slope of the red line. You don't really need fancy math to do that. So if you look at this equation closely, you find that it's nothing but actually an expression for the albedo Coulomb sensitivity that I alluded to earlier, because it's defined as the change of the surface temperature divided by the incoming short radiation multiplied by minus change of the albedo. And now, some of you in the audience probably have realized why this is called a Coulomb sensitivity, because it's basically a climate sensitivity. We normalize the surface temperature change by the forcing of the problem. In this case, the forcing is coming from change of the albedo, right? And it's a local surface climate sensitivity in the sense that the temperature we're looking at is a local surface temperature. Well, in the climate change problem, the temperature that we often look at is the global average surface temperature, while the forcing is usually defined at the top of the atmosphere. But the essence of the problem is the same. We are not trying to look at the problem just from the perspective of how much temperature has been changed. We're looking at the problem from the perspective of the climate sensitivity, how much of the temperature has changed given some amount of forcing. More importantly, with the linearized surface energy balance model, you can connect the local surface climate sensitivity with all these climate feedbacks that we introduce, or heat transfer efficiencies, if you will, in the same way as the climate change literature. So the climate sensitivity is the inverse of the sum of the climate feedback parameters. In climate change, we have water vapor feedback, we have biogeochemical feedback. In this problem, it's simple, we only have four feedbacks, with the Planck feedback being one of them. So now you can see why ACS is not a constant, because all these climate feedback parameters or heat transfer efficiencies are not really constant. So in particular, in the simulations that I showed you earlier, the spatial variability of the ACS, which is plotted on the y-axis, is almost entirely driven by this convective heat transfer efficiency, which is related to the wind speed and the thermal stratification, how much of the heat is taken away by the air, if you will. You can see that a simple model where you only consider the spatial variability of lambda h actually captures the data reasonably well. Not only for one simulation, which is the one that I showed with the red ones, I even changed how the model is configured. So into different configurations, the same relation holds for those different configurations. So I'm not getting into the details. But the way to interpret this curve is that in places where you have very high convective transfer efficiency, imagine in places where you have high wind speed. So, when you blow a fan to your face on a summer day, that's convective transfer. So convective heat transfer takes the heat away from your body. You feel cooler, right? So in places where convective transfer efficiency is very high, the roof already has a mechanism to get rid of its heat through convection. Then the roof doesn't really need to increase its albedo to be cooler. Or in other words, if you really want to increase the albedo of the roof under that conditions, you're not going to get so much of the benefits because the roof is already, taking, the air is already taking away the heat for you. So there's a generated decrease in trend. And it turns out in the simulations that I showed you, that's mostly causing the spatial variability that you've seen. So to quickly summarize this part a little bit, I want to, hopefully this very simple example shows you that we revisit this widely studied problem from a new perspective, a local surface climate sensitivity perspective. And with this linearized surface energy balance model, we can really connect this sensitivity to the heat transfer efficiencies or climate feedback parameters. And we found that the convective transfer efficiency is the key in this problem. And this new concept, what I call the, albedo cooling sensitivity at the surface, is not really meant to replace the albedo cooling effectiveness that we used in the literature. It's really meant to be a stepping stone for us to understand ACEs as well as other changes. As I argued earlier, the source of the cooling is coming from the roof. We cannot understand other things without understanding the roof changes. So now I want to switch gears a little bit to talk about green roofs. And I'll go a bit more quickly because we are using actually a similar approach as you will see in a minute. Just like the white roof effects are very much dependent on the albedo or the reflectance of the white roof, the cooling effects of green roofs or any other green infrastructure is going to be very dependent on how much water you have in the green infrastructure. That's really not too surprising. Again, this is a study that I did when I was doing my PhD, looking at how much of the surface temperature change would be reduced for Baltimore, Washington, as I alluded to earlier. On a typical summer day, the red curve is what my goal was, like 50% of the roofs over Baltimore, Washington area are converted to green roofs. You can see that on the, around noontime, you get about like 1 to 5 to 2 Kelvin degree of reduction in the surface temperature. But that effect is very much dependent on how much water you have in the green roof. If the green roofs are very dry, which is what this green line is trying to show, you barely have any effects. Well, on the other hand, if you are willing to irrigate the green roof a bit more, which is what this magenta line is trying to show, you get actual benefit compared to the baseline case where you just have the green roof, but you don't irrigate. So perhaps we can decompose the problem into a two-part problem. In the first part, we ask the question, how much cooling benefit do we get from a green roof compared to a regular roof if we don't irrigate the green roof? And then how much actual cooling benefit do we get if you actually irrigate the green roof compared to a regular green roof that you don't irrigate? So in a lot of places, especially in drier regions like in Phoenix, the second part of the question is actually more important because you are asking about the trade-off between water conservation, water is precious, you don't want to use it for, all kinds of purposes, versus heat mitigation, right? Heat mitigation requires you to maybe irrigate the green roof, but to irrigate the green roof requires you water. So how do we approach this problem? We can actually use the same approach that we actually showed earlier. Oh, by the way, there have been lots of studies looking at green roofs. So again, mostly from the perspective of the applied perspective, right? We construct the green roof, we do a simulation in Phoenix, we look at the cooling effects, done. We report the change in the temperature. But here I want to actually, add a little bit of like the mechanistic understanding into the problem. So I'm going to change the surface energy balance equation slightly. I want to put the latent heat flux on the left hand of the equation because I recognize that, if I irrigate the green roof, I'm going to probably boost the latent heat flux, which is related to evapotranspiration by the vegetation on the green roof. So in some sense, the change of the latent heat flux can be almost treated as the forcing of the problem, not as the response of the problem. If so, then you can almost, invoke the same kind of like conceptual picture that we used in part 1, that you assume the left is not a function of the surface temperature, the right is a linear function of the surface temperature. The surface temperature has to be at this intersection. If you increase the latent heat flux, you bring down the black line, you reduce the surface temperature. You can do it more rigorously. You can say the water amount that you irrigate on the green roof is Q irrigation, and then the change of latent heat flux, the maximum amount is the latent heat vaporization LV multiplied by the water amount that you put on the green roof, assuming that the water that you put on the green roof, always ends up in the evapotranspiration process, not generating runoff, which you don't want to generate runoff anyway on green roofs. And then the change of the surface temperature is from simple geometry, this term divided by the slope of this red line. So now we have actually a formulation that allows us to actually understand, giving some amount of water irrigation, this is supposed to be the surface temperature change that you should expect. And we can test this model using, again, more complicated tools that we use these days as almost standard tools to evaluate these things. In this case, we're using a global model called Community Earth System Model that has almost a similar structure of the urban model. And in this case, we improved it so that you can have, white roofs, you can have green roofs with irrigation capacity in this model. For the green roof irrigation, for the green roof parameterization, it looks something like this. For those of you who study hydrology, you probably can recognize some of the keywords here: infiltration, irrigation, evapotranspiration, etc. But I'm not going to talk about the details of this parameterization. We tested this green roof parameterization at a green roof site where we compared the simulated surface temperature and soil moisture over a 3-week period, where you can see that you have increase of the water due to rainfall events, not from irrigation, but these are sort of like used to test the model. And you can see that the model works reasonably well, at least for this site. But now that we have the parameterization, we can put the parameterization into the model, and then we can run it, almost at anywhere we want. And we can run the model globally for irrigated and unirrigated green roofs. Because in the computer world, I can do crazy things, right? So I'm going to construct an index called, I'm not going to give a name, but it's the change of the surface temperature divided by the amount of irrigation. Because, I recognize that the more you irrigate, probably the more reduction of the surface temperature that you should expect. So that's kind of obvious. So let's take that away. And that's something that you can compute from the global models, where you can use the irrigated green roof surface temperature minus the unirrigated one divided by the irrigation. And that's the results that you see on here. So let me walk you through. First of all, you can see that some places are blank or white. These are ocean grid cells or land grid cells that do not have any cities or urban fractions. In all the urban fraction, in urban grid cells, we always construct a an irrigated and unirrigated green roof, regardless of whether in reality you have a green roof or not. So that's a hypothetical test. And we always irrigate so that the green roof, whenever, after a day when the soil moisture drops to some, we always bring it up to, sort of the field capacity, which is typically when you irrigate these things. And these are the cooling effects averaged over the June, July, August, the summer season, averaged over 20 years in the historic period from 1981 to 2000, and then averaged over the entire Diurnal cycle. So you are looking at sort of like really a climatological assessment of the effects of green roof irrigation, if you will. First of all, notice that all the results are negative. The values are negative. They are all green, which is good because it tells you that if you irrigate the green roof, you do get actual cooling benefit, or the temperature reduction is stronger. And that's what we should expect. So at least that's consistent with our intuition. Second, you also notice that there's quite a bit of spatial variability that from first sight, we don't really understand. The surface energy balance model that I just showed you earlier provides a way for us to understand this result, because now you can actually use the surface energy balance model to derive this. We just derived it, except now I put the Q irrigation on the left-hand side equation. You can put the latent heat vaporization, LV, also on the left-hand side equation. Then it becomes a climate sensitivity. The LV is actually just a constant for practical purposes, so you can put it almost in any way you want. Now you can see that the model is not perfect, but at least it sort of captures the broad patterns, right? Like in place, the magnitude and the spatial variability looks actually reasonably resembles what the climate model shows. More importantly, the surface energy balance model is easy to understand because it tells you that the green roof irrigation effects are only dependent on two things. One is this latent heat vaporization, which, as I said, is a constant. And then the second thing is all these lambdas. So let's take a look at these lambdas. So in the previous part where I showed you the white roofs, lambda H is everything. You can treat the other lambdas as almost like a constant. Here, you can't treat them as constant, but you can look at the magnitude. So the immediate long wave radiation, or the Planck feedback, is the more familiar one. It's about 6 watts per square meter per Kelvin. That's the feedback parameter that you should get if you are dealing with temperatures on the order of 300 Kelvin. And then the convective transfer efficiency, which is the important one in the first part, again, emerges as a very important one. Its magnitude is on the order of 20 watts per square meter per Kelvin. The conductive heat transfer efficiency is somewhere in between. It's on the order of like 8 to 10 watts per square meter per Kelvin. So you can argue that in this problem, the spatial variability of all three play a role, but in terms of the magnitude, the convective transfer efficiency is very important. So in both of these two examples, hopefully I showed you that we approach the problem from the perspective of local surface climate sensitivity. So you always look at the change of the surface temperature relative to the forcing, and that really helps you to formulate the problem in a more universal way and help you to look at the problem. And the linearized surface energy balance model allows us to link those sensitivities to climate feedback parameters or heat transfer efficiencies. And among them, the convective transfer efficiency oftentimes emerges as really a key parameter. So hopefully with these two examples, I showed you how actually by we actually, I mean myself, gradually moved from looking at the problems from an applied perspective to look at the problems actually from more like a climate science perspective. Now I want to add another example where we look at the effects of anthropogenic heat flux, because I know there are probably some students in the engineering department who study actually building energy consumption, and when one of the climate impacts of building energy consumption is that when you use, for example, air conditioning, you dump the heat exhaust into the outdoor, and that actually exacerbates the outdoor warming effect, or the so-called urban heat island effect. And that's what we call anthropogenic heat flux. So in this problem, it's going to be different because I'm also moving away from the surface. I'm trying to look at the air, because as I alluded to earlier, the air problem is a bit harder than the surface problem, actually, at least in the white truth case. But the anthropogenic heat flux, you can't really distinguish it from the traditional, sort of like the sensible heat flux that we typically measure. So the only way to actually isolate its effects is to do numeric simulations. And that's how people have been doing. You can see that from this list of studies that we compiled, people use different numeric models, look at different cities, prescribe different amount of anthropogenic heat flux. Obviously, Tokyo is probably going to have a lot more anthropogenic heat flux than in nowhere. And you get different amount of temperature change, not too surprisingly, right? So the first thing that I looked at this, my postdoc showed this, I was like, this is not really the best way to look at the problem. We should, at the very least, normalize the temperature change by the amount of anthropogenic heat flux that we put into the model. Because obviously, the more anthropogenic heat flux we put into the model, the warmer the model becomes. It's like the more CO2 we put into the climate model, the warmer it becomes, right? So you should really normalize the temperature change by the forcing that you put into the model, which in this case is, natural is the anthropogenic heat flux, or the building energy consumption. And once you do this normalization, you actually find some quite interesting sort of like consistency across studies with the rule of thumb, value of 0.01 Kelvin per watts per square meter. But there's still some spatial variability and temporal variability. Interestingly, winter, summer difference, as I'll tell you a little bit. So how do we approach this problem? We can use the same energy balance problem. In this case, it's actually quite easy, because if you write an energy balance for the urban canopy air, as in all these models, it's just the anthropogenic heat flux that you put into the air has to be balanced by two convective heat flux. One convects the heat to the upper atmosphere, or the atmosphere above the canyon. One convects the heat to the surface. And since I've already showed you that, oftentimes we use a bulk parameterization for those convective or sensible heat flux, they are actually just a linear functions of the canopy air temperature, which is this TA. So we can actually write the anthropogenic heat flux as a linear function with a slope of lambda 0 multiplied by the anthropogenic heat flux plus some intercept from this equation. And you can derive these lambdas and c's. Again, using a graph like this, you can say, if the anthropogenic heat flux is not a function of the canopy air temperature, which in a lot of these simulations is not, you prescribe it. You say, okay, from some estimate of energy consumption, I know this amount of heat flux has been generated because of human activities. I put it in the model. So it's not a function of the canopy air temperature. Well, the right-hand side of the equation is a linear function of the canopy air temperature. So the temperature has to be at this crossing point. And if you increase the anthropogenic heat flux, you get a new crossing point. In this case, an increased canopy air temperature. And it's, again, the forcing divided by the climate feedback parameter. In this case, the climate feedback parameter is just the sum of two convective transfer efficiencies. But in this case, I want to add a bit more complexity in that the convective transfer might be actually affected by anthropogenic heat flux, because the convective transfer is related to the movement of the air. If you add heat into the canyon, the movement of the air may become more violent. So the convective transfer might actually be enhanced. So this red line might actually become this blue line. So all previous examples I ask you to think, the red line stays where it is. But now, actually the red line might change. So you can see that then the warming effect used to be this red red arrow becomes this blue arrow. So using the words that using the language of climate change, you are introducing a negative feedback that reduces the warming effect that you would have without this negative feedback. So let's think through the process a little bit more carefully. We know the forcing is the anthropogenic heat flux, easy. We know the baseline scenario, we just derive it with the red line states where it is the temperature increase, the canopy air temperature increase and then convects the heat away. So you reach energy balance. But as this process goes on, you introduce more feedbacks. For example, your surface temperature might increase. As the canopy air temperature, surface temperature increase, the surface temperature increase, further increase the canopy air temperature. The heat conductances that we just introduced, one goes from the canopy air to the atmosphere above the canyon, one goes from the canopy air to the surface, might also change. Then the canopy air the air temperature above the canopy might also change, which I'm going to exclude for now. So there are three feedbacks that could be introduced in this whole process. How do we quantify all these feedbacks? So I have three equations, but I'm going to probably skip that. So that I'm going to skip all these feedbacks. But did you teach this in your class? If not, I'm happy to talk about how we actually quantify these feedbacks with them. But I'm going to jump just to the results to show you, like, once we are able to quantify these actual feedbacks, what would be the results? You're looking at the simulations that we did over corners at a resolution of about 1/8 degree, which is about 12 kilometers. Every place that you see that has a color means that we add an anthropogenic heat flux into the model, and then we are trying to assess how much warming that anthropogenic heat flux has caused in that grid cell. But you probably can't see much of the spatial variability, so I'm going to ask you to just focus on the value on the top right, which is the median value across corners. And all of these are so-called climate feedback parameters. So on the left column is the summer season, on the right is the winter season. These are, again, averaged over the entire Diana cycle, averaged over 20 years in the historical period, a climatological assessment. The top row is the total feedback parameter. And that's inversely related to the climate sensitivity with a minus sign. So now you can see that we have an understanding of why our climate sensitivity is always on the order of 0.01 Kelvin per watts per square meter, as in the literature, because the total feedback parameters in summer and winter are almost always on the order of like minus 100. For the summer it's minus 122, for the winter it's minus 111. So good, that's consistent with the literature. So we got at least the first one correct. If you look at the baseline, which is, this red line states where it is, this scenario, you can see that you almost get half of the story, especially for the summer. You can almost explain the total climate sensitivity with just the baseline scenario. So once you know the baseline, you know half of the story, except that you can't really separate or you can't really understand the winter-summer difference, which is the key in this part. So for understanding the winter-summer difference, you really have to look at the new feedback parameters that we introduced. As I alluded to, one is the surface temperature. So as the canopy air increase, the surface temperature increase. As the surface temperature increase, the canopy air further increase. And then the heat conductance between the air and then the atmosphere above the air is a negative feedback, which is what I also alluded to. When the red line becomes the blue line, you essentially, you convex more heat out of the canyon. So you have more heat ventilation out of the canyon. So the warming effect within the canyon gets less as the convective heat transfer becomes more efficient. In the summer, these two effects tend to cancel each other. That's why the baseline scenario is almost like the total feedback. While in the winter, it's the negative feedback from this convective transfer efficiency gets inhibited a little bit. So the positive feedback from the surface temperature wins over, which is why in the wintertime effects of anthropogenic heat flux tend to be stronger than the summertime effects, because you have a positive feedback that wins over the other negative feedbacks that adds a little bit of the sensitivity to the problem. So the last thing that we learned is that the heat conductance between the canopy air and the surface is not really a lot of contribution. And that's good because that's reassuring to our analysis, because we know in the model this conductance is not really affected by the thermal stratification much. So the fact that it doesn't really play a role is actually telling us that our diagnosis is probably correct. So hopefully with all these three examples, I convince you that this like linearized energy balance model, sometimes you don't even need to linearize it with the last example, really provides a nice way for us to understanding some of the problems that we often deal with in urban climate, especially related to heat mitigation. And all of these examples show that the convective transfer is really a key, which is related to the other side of my research, which focuses more on the fluid dynamics in cities. But I'm not going to talk about those. But really what I want to emphasize in this talk today is that the concepts like climate forcing, feedback, and sensitivity should be embraced in our urban modeling research. In addition to looking at things through the lens of applied research, which is important, we should also try to look at the problem through the lens of science. That helps us to actually restructure the problem, actually learn something out of all these amazing examples that we have encountered in our urban climate research. With that, I'll stop and I'm happy to take any questions.